In today's class, we will go through one very important reaction of aldehydes and ketones. It is aldol condensation, right? So let me write it down. It's aldol condensation, right? So as the reaction is a condensation reaction, we know that in condensation reactions, two or more molecules will react, right? They will undergo self-condensation with the elimination of a simple molecule like water, ammonia or HCl, right? So similarly in aldehydes and ketones, two same or different aldehydes or ketones will undergo self-condensation. That is, when they react, they combine with the elimination of water molecule, right, to give you beta hydroxyaldehydes or ketones, right? So here, then we'll see why we call it as aldol. This is important to understand. So here, your aldehydes or ketones, right, will undergo self-condensation in the presence of dilute sodium hydroxide. This is important to mention in this reaction, that this reaction takes place in the presence of dilute sodium hydroxide. And what this sodium hydroxide will do, we'll see that in the mechanism of this reaction. So aldehydes and ketones will undergo self-condensation, right, to form beta hydroxy aldehydes or ketones, right, with the elimination of water molecule. This is your aldol condensation, right? Now the other thing to understand here is, if this aldol condensation is taking place between same aldehydes or ketones, right? For example, if this condensation reaction take place between two molecules of acetaldehyde, then this is known as aldol condensation or simple aldol condensation. Whereas if the same aldol condensation, right, is taking place between two different aldehydes, that is, one molecule is of ethanol, the other molecule is that of propanol. So these are two different aldehydes. In this case, when you have two different aldehydes or ketones, we call it a crossed aldol condensation, right? So here, and this reaction can also take place between an aldehyde and a ketone, right? Then also it is known as your crossed aldol condensation. So if the reaction is taking place between same aldehydes, same aldehyde or ketone, this is your simple aldol condensation, right? If you have different aldehyde or a ketone, then this is known as your crossed aldol condensation, right? Now there is one very important condition, requirement for this reaction, that these aldehydes and ketones that we are talking about that will undergo this condensation reaction, they should contain alpha hydrogens, right? So these aldehydes and ketones should contain alpha hydrogens, right? These should contain the alpha hydrogens. Now that means, what is an alpha hydrogen? If you remember, this is your CH3CHO, right? This is your carbonyl carbon, right? The carbon which is next to carbonyl carbon is your alpha carbon, right? And hydrogen atoms attached to it are your alpha hydrogens, right? These are alpha hydrogens. So only those aldehydes and ketones that contain hydrogens attached to alpha carbon, which are alpha hydrogens, will undergo aldol condensation. What they do in the reaction, we'll see that while doing the reaction, right? Now if you look at this HCHO, this is your formaldehyde. Formaldehyde, if you see, it does not contain alpha hydrogens because there is no carbon next to or connected directly to this carbonyl carbon, right? So no alpha carbon means no alpha hydrogens, right? Since you do not have any alpha hydrogens, right, no alpha hydrogens in formaldehyde, so formaldehyde will not undergo aldol condensation, but it can take part in crossed aldol condensation, right? And it makes aldol condensation, it makes your crossed aldol condensation useful. It makes it a better reaction. How it does that, we'll see that in the reaction, right? So normally this formaldehyde that does not contain alpha hydrogens will not undergo aldol condensation, but it can take part in crossed aldol condensation, right? Now let's look at the reaction. Let's look at the reaction. This is your acetaldehyde, right? We'll just look at the simple aldol condensation between two aldehyde molecules, right? Now right, since this is a reaction between two aldehyde molecules, condensation reaction, right? So this alpha hydrogen, like I said, the aldehyde should contain alpha hydrogen. This alpha hydrogen will go and join this oxygen, right? And the product should be beta hydroxyaldehyde or ketone. Now why we call it a beta hydroxyaldehyde or a ketone, we'll see that. In the presence of dilute sodium hydroxide. This reaction occurs in the presence of dilute sodium hydroxide or dilute alkali. You may take calcium hydroxide in place of this or sodium carbonate, right? So the product would be, when this will go here, it would be CH3COH, right? You have CH, C double bond OH, right? Now this is your carbonyl carbon, this is your alpha carbon, this is your beta carbon. Since your OH group in the product is directly connected to your beta carbon, so that is why we call it a beta hydroxyaldehyde, right? This is your beta hydroxyaldehyde, right? You have an aldehyde group here and you have hydroxy group attached to the beta carbon atom, so this is your beta hydroxyaldehyde. Now another important thing about this reaction is that this beta hydroxyaldehyde or ketone, in the presence of dilute acids, dilute hydrochloric acid, will undergo dehydration. It will lose a molecule of water to form a stable product, right? The product which is more stable than this beta hydroxyaldehyde, right? So in presence of dilute HCl, right, this will undergo dehydration, right? A molecule of water would be eliminated, right? I have missed one, it will go here, I missed one hydrogen here, I'm sorry, right? So it will form this compound. A molecule of water would be eliminated, it will form this compound. This is your unsaturated aldehyde. This is your unsaturated aldehyde, right? Now we said that this reaction will take place easily because this compound is more stable than this beta hydroxyaldehyde. That is, this unsaturated aldehyde is more stable than your beta hydroxyaldehyde. Why? The reason being is, if you look at this compound, right, you have, this is your conjugated compound, right? This molecule is conjugated. Conjugated means in the molecule you have alternate double and single bonds. If you look at this, this is single, this is double, this is single, then again you have double. So this is a conjugated molecule, right? So due to conjugation, this unsaturated aldehyde is more stable than your beta hydroxyaldehyde, right? So this is more stable, conjugation, due to conjugation, due to conjugation, product, that is this unsaturated aldehyde, is more stable. Right? This is important to remember. So this is your aldol condensation, right? Basically. Now you can do the similar reaction between two different ketones, right? Or between two same ketones and different ketones is your cross aldol condensation. We'll see that in a moment. So let's quickly take the reaction between two different ketones, CH3CO, then you have CH3, right? Plus you have this right. Two molecules of acetone will undergo condensation. This is your alpha hydrogen. It will go to this oxygen. Product would be CH3, COH, CH3, CH, H, then this is the product, right? And you can see this is your beta hydroxy ketone. You have a ketone group here, and this is alpha, this is beta. At beta carbon you have OH group. So this is your beta hydroxy ketone, right? Now this beta hydroxy ketone will undergo dehydration in the presence of dilute acid, same as this. In the presence of dilute HCl, it will undergo dehydration, right? So a water molecule would be eliminated like this. It will form CH3, right? CH3 double bond CH, right? This is the product, and this is your unsaturated ketone, right? This is your unsaturated ketone, and you can see you have, this is a conjugated molecule. This compound is conjugated. That is why this is more stable than your beta hydroxy ketone. You have a system of alternate double and single bond. This is your single bond, double, single, then again double, right? So this is more stable than this, right? I hope this is clear. And now we'll understand why we call it as aldol. In any of the product, if you look at this product, right, it contains an aldehyde group, it contains a OH group, right? This is aldehyde, ALD, this is OH. That OH is your alcohol, OL, right? So that is why we call it because this product, your beta hydroxy aldehyde or a ketone, basically this name is taken from this beta hydroxy aldehyde only, right? So because it contains, if you look at this product, it contains your aldehyde group CHO, right? And it also contains your OH, alcohol group, right? So CHO is for aldehyde, right? So ALD is from aldehyde, right? And your OH means, OH is alcohol. For alcohol we use OL, right? Plus OL. So this will make it aldol. That is why we call it as aldol condensation. The word aldol is taken from the product of the condensation of two aldehydes, right? Which is your beta hydroxy aldehyde. Since this beta hydroxy aldehyde contains your aldehyde group and your hydroxyl group, we call it a aldol. This product is your aldol, right? So this product is nothing but aldol. Just remember, both these react to form aldol, right? And you have your IUPAC names of these compounds that you can check in your books, right? So now let's look into the mechanism of this reaction, right? The mechanism is important. This product is your mesithyl oxide. right? And you can give the IUPAC name also to this. This is 4-methyl. If you look at the compound at 4th position, right? 1, 2, 3, sorry, 1, 2, 3, 4, right? Or 4-methyl, right? 3N. 3N means at 3rd carbon atom you have a double bond, right? Then you have your 2-on. If you number it like this, 1, 2, 3, 4, 5. Right? If you number it like this, the name would be 4-methyl. Right? Firstly, you have 5 carbon atoms, so this is pent. Right? So at 4th position, you have this substituent. Substituent always go at the prefix. So 4-methyl pent. At the 3rd carbon atom, you have this double bond. Right? 3N, ENE. Then at the 2nd carbon atom, you have ketone group, for which you use ONE. Right? This is how you name it. So this would be 4-methyl pent 3N. 4-methyl pent 3N 2-on. This is the name. This is IUPAC name. So you can look in your books for your IUPAC names, right? So in this, the important thing is your simple aldol condensation, the reaction between same aldehydes. Crossed aldol condensation, if aldehydes are or ketones are different, we'll look at this reaction. And the most important thing is that these aldehydes and ketones should contain alpha hydrogens, right? And like formaldehyde does not have alpha hydrogen, so it will not undergo aldol condensation, simple aldol condensation, right? Now, the product of condensation of 2 aldehydes would be beta hydroxy aldehyde. Now this beta hydroxy aldehyde, since it contains aldehyde group and your alcohol group, right, we call it as aldol because it contains your aldehyde group and your OL group, right? So ALD and OL, like I explained here, right? Now this beta hydroxy aldehyde or ketone is less stable, so it will easily undergo dehydration reaction in the presence of dilute acid to give you this conjugated compound. Right now, due to conjugation, this unsaturated aldehyde or a ketone is more stable. Right? Just remember all this. Now let's quickly look at the mechanism of aldol condensation. Right? Now mechanism is, in this mechanism, we will see how this alpha hydrogen and this sodium hydroxide, right, takes part in the reaction. Right, so mechanism, it's a simple mechanism of 3 steps. In the mechanism, this OH from this dilute alkali will abstract a proton, will abstract this alpha hydrogen, right, will abstract this alpha hydrogen from the molecule of aldehyde, right, forming enolate ion, which is a nucleophile. Then that nucleophile will attack the other molecule of aldehyde at its carbonyl carbon, because we know that nucleophile is negatively charged and your carbonyl carbon is positively charged, right? So let's look at the reaction. Right, you have this OH, right, that will, right, this OH will remove a proton, right, from one molecule of aldehyde, right? So when it will remove one atom of hydrogen, this is your alpha hydrogen. So basically this alkali, the OH group from alkali will remove one alpha hydrogen, right? It will remove one alpha hydrogen to form this enolate ion, right, which is stable due to resonance, right? It will form this enolate ion which is stable due to resonance. It will leave its, when it will depart, it will leave the bond pair of electron with it. Now this is stable due to resonance, right? If you look at this, this will move to here, right? So it will form CH2 double bond CO minus, right? So this is your enolate ion, which is stable, which is more stable due to resonance, right? Because this bond pair, this pair of electron will move, right? And the other form is this. Now this enolate will attack the other molecule of aldehyde at its carbonyl carbon, because we know that this is your nucleophile. Now this enolate ion will act as a nucleophile, right, and will attack the other molecule of aldehyde, because this reaction, if you remember, is taking place between two aldehydes or ketones, right? So this is your, if you remember the carbonyl chemistry, this is your carbonyl, right? And oxygen is more electronegative, so it will pull the pi electron towards itself, giving it a small negative charge, and this carbonyl carbon will get a positive charge. So now this enolate ion will attack at this carbonate, which is positively charged, right? So now let me show you that, right? 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 So this is basically your nucleophilic attack. Right? Where it forms when this nucleophile will attack at this carbonyl carbon. It has a small positive charge, a small negative charge, right? It will form a anion. Sorry. Right? This will join to this carbonator, right, to form a anion. Right? Now it will join here. This is the anion. Right? Now this anion will abstract a proton from water. This is the anion, right? This anion will abstract a proton from water. Just understand this step. This is your nucleophile, right? Now this nucleophile will attack this carbon atom, which is positively charged, because nucleophiles will always attack organic compounds at points of or at sites of high electron density. So it will attack here, it will form this anion. Now this anion will take a proton from water, right, from the solution, to form your beta hydroxyaldehyde. Like this, right? It will take up a proton from water solution, right, to form beta hydroxyaldehyde. This is the mechanism of the reaction. It's a simple 3-step mechanism, right? I'll repeat. Since this reaction takes place, we discussed in the presence of dilute alkali, right? In the presence of dilute sodium hydroxide. So OH from this dilute alkali will abstract or remove a proton, right, from one molecule of aldehyde. That is, it will remove this alpha hydrogen, right, without which we said this reaction will not take place, right? So here you see that how this alpha hydrogen has taken part in the reaction, right? When this alpha hydrogen would be removed, right, it will form a nucleophile which is enolate ion. Now this enolate ion is more stable due to resonance. These are the two resonance forms. Now this nucleophile will attack the other molecule of aldehyde, because this reaction is between two molecules of aldehydes. Now this nucleophile will attack the other molecule of aldehyde at the carbonyl carbon. Why at carbonyl carbon? Because carbonyl carbon is positively charged, and nucleophiles which are negatively charged will always attack at positive sites. Here the positive site is the carbonyl carbon. And why this is positively charged? Because oxygen is more electronegative in carbonyl compounds, right? So this oxygen will acquire, or this oxygen will attract the shared pair of electrons more towards itself, giving it a small negative charge, and carbon will acquire a small positive charge, right? So now it will attack here to form this anion, right? Now this anion will take a proton from water to form this beta hydroxy aldehyde, right? Which is your aldol. Aldol. It contains aldehyde group and it contains OH group. That is why we call it a aldol condensation. So this is how this reaction goes. Now in the next lecture we'll talk in little detail about crossed aldol condensation. But I'll just give you an overview of what is your crossed aldol condensation. Right? I'll just remove this. Stop this off. Like I said in the beginning, that crossed aldol condensation is a reaction. Crossed aldol condensation is a reaction between two different aldehydes or two different ketones, right? And they should possess alpha hydrogens. In this case, the other aldehyde, one aldehyde can contain alpha hydrogen and the other may or may not contain alpha hydrogens, right? Now we'll see how the two reactions differ. Suppose we take two different aldehydes, CH3, CH2, this. If the reaction takes place between two different aldehydes, this is your crossed aldol condensation. Now, how this reaction will take place? In this reaction, you will get multiple products, right? Since you get multiple products, it is difficult to separate those products, right? That is why this reaction is not of much value from synthetic point of view. From the point of making compounds, this reaction is not very good, right? Because if I do this reaction, first these two molecules of aldehyde will react. Let's say this acetaldehyde, let's say this as ethanol, ETH, let's call this as propanol, right? Now how this will react, I'll just quickly tell you, then we'll make another lecture on this. Two molecules of ethanol will react to form one type of aldol, which is your beta hydroxyaldehyde. Now then two molecules of propanol, aldehyde one say propanol, will react to form other beta hydroxyaldehyde. That would be an aldol, say aldol 2, right? Then one molecule of ethanol will react with propanol, right? In this reaction, the alpha hydrogen, right? The alpha hydrogen, that is this hydrogen, the alpha hydrogen would be from this. The alpha hydrogen will come from propanol, that will go to oxygen of this carbonyl carbon, of the oxygen of this ethanol, that is this, right? So as I said, that alpha hydrogen from this propanol will come, right? And if this is like this, right, it will go to this, you will get aldol 3. Then propanol, other reaction would be propanol will react with ethanol. In this case, alpha hydrogen will come from ethanol, then you will get aldol 4. So you get 4 products on this in this reaction, right?